All right, everybody, welcome to Math with Grace. Today we're going to be working through Pre-Calculus, Unit 4, Section 2. Section 2 begins on page 31, and it's titled Inverse Trigonometric Functions and Inverse Functions. Looking down here at the bottom of the page, it says the inverse of a function f to the negative 1 of x has been defined as a function resulting from the interchanging of the domain and the range. Okay, we've kind of worked with the sign to the negative 1, right? But that was the reciprocal function, so we don't want to confuse the reciprocal functions with the inverse functions because they're not the same thing. Forming the inverse of a function, however, does not always result in a function, and they go through an example of just some ordered pair numbers. Remember, when we take the inverse of the function, it's not a function if we have multiple x or the same x value with multiple y values. Like here, we have x is 1 and x and y is negative 1. Here, x is 1 and y is 1, and so these don't work. Same with the 9s. 9 comma negative 3 and 9 comma 3, so it's no longer a function. Now it says here in the second column, let's consider a few solutions to f of x equals the sine of x, right? So here's our normal chart, very useful for us to be doing our work with, right? I believe this is on page 6 as well, and we've been using that as a reference going forward. Let's turn the page. Here at the top of page 32, we see that to form the inverse, we interchange the range and the domain. So now they've swapped them back and forth, and it ends up looking like this, right? But if we did a vertical line test, we could see that this is not a function the way it is written, okay? It says, note that the range of the sine function between negative 1 is less than or equal to y, which is less than or equal to 1, now becomes its domain. Okay, or the domain of this inverse. Another name for the inverse sign is arc sign. When you're talking about inverse functions, y equals the sine negative 1 of x means the same thing as saying y equals the arc sine of x. So we'll go forward saying arc sine, okay, because it gets a little confusing otherwise. Looking here still on page 32, second column, it says, note that this inverse is not a function because there is not a unique y value for each x. In order to be able to call the arcsine relation a function, you must have one and only one y value for each element of the domain. Look at the following graph. If you restrict the range, let me slide up here. If we restrict our range so that negative pi over 2 is less than or equal to y, and that is less than or equal to positive pi over 2, then we have a function because we're only taking a chunk of this inverse sign, okay? So now we actually have a function. Back, I'm going to top of page 33. I wish I could get it to fit all in, but it says, because of this restriction on the range, when evaluating or simplifying expressions involving the arcsine function, there will now be one and only one correct answer because we're going to be restricting that range. We're working in a smaller piece of the graph, okay? It says, note that on the inverse sine function, for x values from 0 to 1, the angle measures are from 0 to pi over 2. For x values from 0 to negative 1, the angle measures are from 0 to negative pi over 2. For the x values less than negative 1 or greater than 1, there are no angle measures, okay? So if the arcsine of x then, if we have y equals the arcsine of x, then negative pi over 2 is less than or equal to y, which is less than or equal to 0, for negative 1, which is less than or equal to x, which is less than or equal to 0. And then we have the opposite is true for 0 to 1. And it says here there are no solutions for x is less than 1 or x is greater than 1. Okay, that's an important thing to remember. or at least be able to come back and evaluate again. All right. Here's our first example. First column, page 33. Evaluate the arc sine of the square root of 3 over 2. So it says you must find a first quadrant angle whose sine is the square root of 3 over 2. So since pi over 3 equals the square root of 3 over 2, and now you can find that here, right? So we are looking for a first quadrant angle, whose sine is the square root of 3 over 2. So square root of 3 over 2, right here, in our unit circle. This is from Unit 2, page 99. It's very useful. I've been using it this whole book here. So if you don't have a copy of this for yourself, you should make one. It's in Unit 2, page 99. So the sine is the second value in our little coordinate here. So the sine of square root of 3 over 2 is right here, first quadrant. The angle measure is pi over 3. Okay, that's how they got this. Since the sine of pi over 3 is the square root of 3 over 2, the arc sine of the square root of 3 over 2 is pi over 3. Okay, the answer is pi over 3. It says note that while 2 pi over 3 also has a sine of the square root of 3 over 2, which is right here. Oh, that's 4 pi over 3. Oh, right here. I missed it. It's a little blurry on mine. I need to make a better copy. Square root of 3 over 2 is also 2 pi over 3. It's not in the range of the arc sine. Okay? Remember, we talked about our range being very specific. So it's not in the range anymore. It's not going to work. It's greater than pi over 2, right? So we're not taking that one. So the only answer is pi over 3. All right, so this unit circle is going to be very useful in this section, as it has been for a while. Let's take a look at this next example, the top of page 33, second column. It says, evaluate arc sine of negative square root of 2 over 2. Let me grab my unit circle again. It says the reference angle whose sine is the square root of 2 over 2, right here, square root of 2 over 2, is pi over 4. Since you're evaluating the arc sine of a negative value, see, we have a negative here, the angle must be negatively rotated acute angle, right? So now we're looking for negative square root of 2 over 2, which is down here, either one of these technically, okay? And so it becomes the negative pi over 4. That's our reference angle. Negatively acute angle would be a negative pi over 4. So if we just solve this one for pi over 4, and then because we're dealing with the negative, then we just make it negative. That is our reference angle, because even though it would work for pi over 4, right, and 7 pi over 4, or not 7 pi over 4, those aren't the reference angle. The reference angle is pi over 4, so they just made it negative. It says you can evaluate expressions involving the composition of functions. Remember, that's multiplying them together. We evaluate their composition of functions from right to left, or working from the inside of the function out. Okay, so now let's take a look at those. Simplify arc sine times the sine of 40 degrees. Well, the thing about a problem like this is the arc sine is technically kind of the opposite of sine. So if it says the arc sine of the sine of 40, the answer is just 40. These cancel each other out, and we're just left with the 40 degrees. Okay, so those are kind of basic. Here, it says the arc sine of the sine of 120, so you'd want to say, oh, well, it's 120. But remember, we need the reference angle. The reference angle is how we solve these things. So since 120 starts here, right, and it goes this way, looks like this. The reference angle is how much farther it takes to get to this 180 line. So the reference angle is 60 degrees. All right, so it is a 60-degree angle. All right, does that make sense? Remember, we want our reference angle. And it says here that note the angles in the range of arc sine must be between negative 90 and positive 90. And since 120 doesn't fall in this range, we have to find the other angle that does, and that's the 60 degrees. Okay, so it's a 60-degree angle. All right, let's turn the page. There's a good reminder up here at the top of page 34. It says use radian measures, right? 120 degrees is the same as 2 pi over 3. 2 pi over 3 is a second quadrant angle with a reference angle of pi over 3. So if we were to find the arc sine of the sine of 2 pi over 3, remember these kind of cancel each other out, but we still need to find the reference angle. So just like we can do it with degree measures, we can do it in radian measures, and that's just like a review of that, okay? Looking here at this next section or next part, it says the inverse of the cosine function. It says just like the inverse of the sine, the inverse of the cosine is not a function, okay, unless you restrict the range. Here we restrict the range a little bit differently. We restrict the range to 0 and pi. So 0 is less than or equal to y, which is less than or equal to pi. Okay, that's the restriction that we put on. So at the top of the second column on page 34, our first example here says, simplify the arc cosine of the cosine of 5 pi over 4. Where's my unit circle? 5 pi over 4 is a third quadrant angle, okay? And it has, which is right here, it has a negative cosine value. It's negative square root of 2 over 2. Note that 5 pi over 4 is not in the range from 0 to pi, okay? Here's 0 and here's pi. 5 pi over 4 does not fall in this range, because it's in quadrant 3, sorry. Find an angle in quadrant 2 where the cosine is negative. The angle must have the same reference angle as 5 pi over 4. So what is my reference angle for 5 pi over 4? Well, 5 pi over 4 is 1 past, right? This pi is technically, you can consider it 4 pi over 4. So this is 1 pi over 4 too far, or its reference angle is pi over 4. Now, to find the positive pi over 4, we're starting at our pi, which is 4 pi over 4, right? That's how we get 1. And take 1 pi over 4 away. So now we're at 3 pi over 4. There we have a positive angle, and it's for 3 pi over 4. So the arc cosine of the cosine of 5 pi over 4 is 3 pi over 4. All right, reference angles are important. We're going to be working with them a lot. Okay, next example. Evaluate the arc cosine of 5. All right, 5 is not in the range of the cosine function, right? Cosine doesn't ever go over 1. Therefore, it is not in the domain of the inverse cosine function. So this is an undefined or a not defined problem. All right. Okay, let me set this aside so we can look at our next part here, which is the tangent function, or the inverse of the tangent function. It's a reminder here that tangent's positive in quadrants 1 and 3. Top of page 35, it says recall the graph of the tangent function. Looks like this, right? Over and over and over. It says if y equals the arc tangent of 1, the solution set is infinite. It goes on and on and on. And here is what it would look like, okay? Now it says if we restrict, because these are going to be stacked on top of each other, right? Because if you are taking the inverse, you're basically turning this like this. So they're going to be just stacked on top of each other, right? So obviously we don't want that, because now they're not functions, okay? So if we take the range from negative pi over 2 is less than y, which is less than pi over 2, then we can get one continuous thing that actually has a domain of all real numbers, because this arrow goes on and on forever, amen, getting closer to pi over 2 but never crossing it, right? Because that's where our asymptotes are. It says the range includes the entire period of the tangent function without repeating and is symmetrical around 0, or the x-axis. All right. Top of page 35, second column, it says when you evaluate the arctangent function, the values must fall between negative pi over 2 and pi over 2, the y values, okay? So evaluate the arctangent of negative 1. It says your answer must fall in either 0 to pi over 2 or negative pi over 2 to 0 quadrants, right? Tangent is negative in the fourth quadrant only, because remember, in the first quadrant, everything is positive. Since pi over 4 has a tangent of 1, negative pi over 4 will have a tangent of negative 1. So the arctangent of negative 1, the arc whose tangent is negative 1 is equal to negative pi over 4. And I don't have, there was like a little chart, I think, in book 2 where they had the values for sine, cosine, tangent, right? I'm pretty sure that's in book 2. I'll go look in a second. But we're looking for a tangent. The arc whose tangent is negative 1, right, is going to be negative pi over 4, because right here is our cosine and our sine. Tangent is sine over cosine. And pi over 2 divided by pi over 2 is the same as, or sorry, the square root of pi over 2. The square root, oh my gosh, the square root of 2 over 2 divided by the square root of 2 over 2 is the same as the square root of 2 over 2 times 2 over the square root of 2, and so that's our 1, right? This becomes our 1. That's how they figured out it's pi over 4. And so the reference angle would be a negative pi over 4 down here. Same thing right there. This becomes a negative 1. All right. Let me see if I can find that other chart real quick. So I actually found the chart here in, where are my pencils? In Unit 3. Unit 3, page 75, has this little chart, which I would suggest making a photocopy of and keeping with you as well as a reference while you're doing this work. Because if we look back at this problem, the arc tangent of negative 1, right? The tangent is positive 1 at pi over 4. So to be a negative 1, it would be negative pi over 4. Okay, so again, the unit circle, super valuable. I don't think this book has a copy of it in the review section. That's in book 2, page 99. Book 3, page 75 is this chart here, which is also going to be very useful. So use the resources that you're given because they are helpful. All right, on with these problems. Example here, page 35. Simplify the tangent of the arctangent of 2. Now again, the tangent of the arctangent, these are kind of opposite things. It says this means that A is an angle with a tangent, so it says let A equal the arctangent of 2. So that A is an angle whose tangent with a tangent of 2. Okay? So an angle whose tangent is 2 and the tangent of 2, the answer is 2, right? They cancel, these things cancel each other out and the answer is just 2. All right? They try to get a little trickety with us, but we're going to work through it. This next example says the sine of the arctangent of 2. So now remember, 2 is the domain of the arctangent. So this one we kind of have to map out a little bit. So where do we have a tangent of 2? Well, remember, tangent is equal to sine over cosine, or opposite over adjacent, okay? So they set up a little angle. If we have an angle whose opposite is 2 and adjacent is 1, then we will have a tangent of 2, right? The angle whose tangent is 2. This is what this looks like. Now, to solve for the sine of this, though, we need to get the hypotenuse. Using the Pythagorean theorem of 1 squared plus 2 squared equals c squared, right? We get that c is equal to the square root of 5. That's this, the hypotenuse, right? So now we can find the sine. The sine is going to be opposite over hypotenuse, or 2 over the square root of 5, which we cannot leave that way because we cannot have a radical in the denominator. So we're going to multiply this by 1 in the form of the square root of 5 over the square root of 5. Okay, so we get 2 to the square root of 5 over 5, right? That's what this simplifies to. So the sine of the arctangent of 2, because they don't cancel each other like this example, right? We actually have to do the work, is 2 times the square root of 5 over 5. Done. Okay, let's turn the page. All right, on page 36, taking a look at some of these problems together, starting with number 2. Evaluate the arc sine of 1/2. Or basically they're saying the angle whose sine is 1/2. Well, what angle has a sine of 1/2? Looking at our unit circle, remember the sine is the second part of these ordered pairs, and here's a 1/2. The angle whose sine is 1/2, these are all radian measures, so we'll use that, is pi over 6. All right. For number 3, I'll just leave the unit circle there for right now. The arc sine of the sine of pi over 6. Okay. Remember, the arc sine and the sine cancel each other out. Sorry, I read that wrong. Simplify the arc sine of the sine of 6 pi. Okay. My bad. Now, 6 pi is not in the arc sine range, right? It's far out of the range, but we can still kind of simplify this. The sine of 6 pi is just a multiple of 2 pi, right? 1 time around is 2 pi, 2 times around is 4 pi, 3 times around is 6 pi. The sine then of 6 pi is 0. So the arc sine of 0 is 0. Letter A. Okay. 2.4. Simplify arc sine of the sine of negative 3 pi over 2. Negative 3 pi over 2 is outside of our range, so we can't really use it. But if we look here, 3 pi over 2, right? Negative 3 pi over 2, since this is a negative, right? Instead of going this way and stopping here, would go this way and co-terminate with pi over 2. Okay, remember, negative angles go the opposite way, right? So a positive 3 pi over 2 would go counterclockwise. A negative 3 pi over 2 would go clockwise and co-terminate with this pi over 2. And so the answer is C, pi over 2. Because that is actually in the range of what we're looking for. All right, next I'd like to take a look here at problem number 7. Evaluate the arc sine, or arc cosine of negative 1. Well, if we grab our unit circle back here, put it over here, I guess. Knock down everything else here. All right. We are looking for the arc cosine. Remember, that's what this represents, of negative 1. Well, it's the angle whose cosine is negative 1. On our unit circle, cosine is the first set of terms in our unit, or in our ordered pairs, right? So here's our negative 1. So where our cosine is negative 1, our angle is pi. So letter D is the answer. Okay, I'm going to slide this over so I can keep my unit circle kind of on screen here. All right, simplify the arc cosine of the cosine of negative 120 degrees. Okay, we are going to be looking for a reference angle here. We need to find out where our negative, remember negative means we're going this way, okay? Negative 120 degrees, positive 120 is right here, right? come up here, positive 120 degrees is this setup. So we're down here, kind of, this is where we ended up. The cosine of that is at negative 1/2. Now, negative 120 degrees, or 4 pi over 3, however you want to look at it, doesn't fit into our range, right? So we have to find the value that is actually going to work and fit inside of our range. And that is up here. See how it goes right across? Okay. Positive, this was a negative 1/2. We need the positive because it's the only way it's going to work. And that is going to give us an angle of 60 degrees. Now, 60 degrees is the reference angle of negative 120 anyway, right? If we came this way, negative 120 gets us to be right here. The reference angle, because reference angles are always positive, right, would be 60 degrees. So the answer is C. Let's take a look at number 9. It says simplify the sine of the arctangent of 3 over 4. Now, if we think of our tangent, remember our tangent is sine over cosine, or opposite over adjacent. So that tells me that this is 3 over 4, right? To get the sine of that, we have to solve for our hypotenuse of this triangle, okay? Which is going to be 3 squared plus 4 squared equals c squared, or 9 plus 16 equals c squared. 25 equals c squared, square root of both sides, c equals 5, okay? So now we can find the sine of the solution, which is going to be opposite over hypotenuse, or 3 over 5, which is letter C. All right, you go ahead and finish the rest of these problems on your own, and meet me back here for the next part of section 2. This next part of section 2 begins on page 38, and it's called inverse reciprocal functions. So remember, the reciprocal is cosecant, secant, cotangent, not cosecant, yeah, cosecant, secant, tangent, and the inverse of them is what we're talking about now, okay? It says, understanding the connection between a function's equation and its graph can make graphing more efficient. The cosecant function is the reciprocal of the sine function, and they are graphed here on the same axis, okay? Looks like this, and this, the blue, is the cosecant. Looking at this graph here, we see that the cosecant has asymptotes at multiples of pi, where the sine function would be 0, right? Because if we take the reciprocal of that, then we have an undefined term. Moving up here to the top of page 39. It says, because the cosecant function is periodic, like the sine function, you will need to restrict the range of its inverse, okay? So, cosecant, sine, the inverse cosecant is something different. Consider the interval of the domain of the cosecant function from negative pi over 2 to pi over 2 from the inverse by reflecting it over y equals x. So this green line is y equals x. The orange is the cosecant. The red, or pink, or whatever color this is the inverse cosecant, okay, or the arcsecant. Now, unfortunately, this graph isn't really graphed correctly. So I've kind of drawn in, not that it really matters, but it just was bothering me. I've kind of drawn in the correct placement of these parts, because if we look at the graph on page, in this review section, let's see what page it's on, 56, okay, it gives us the cosecant and the cotangents and all of those things. And you can see that when we are at pi over 2, we should be at 1. And so when we are at pi over 2 here, we should be at 1. And when we switch it around, pi over 2 is basically 1.5, and 1 then would be like right here. So I used this chart here on page 56 to make the adjustments here. Again, you don't need to necessarily change yours. They're just trying to show you what it would look like when we switch the x and the y, okay? Remember, the sine, the cosecant is 1 over sine, right? That gives us this blue thing. The arc cosecant is when we switch the x and the y. So it actually becomes reflected across the y equals x axis. It's a little bit different. It's a little bit confusing, but it's a little bit different. We're going to take it nice and slow. Okay? Continuing here in this first column, it says, since 0 is not in the domain of the cosecant of x, it is not in the range of its inverse, the arc cosecant of x. The x-axis is an asymptote in the graph of y equals the arc secant of x, right? The x-axis becomes an asymptote. This line will approach it forever and ever and amen, but never cross it. Same here with this one that comes up, okay? All right, looking at the example, top of page 39, second column. Simplify the arc cosecant of the square root of 2. All right, it says you are finding an angle in the range of 0 to pi whose cosecant is 2. The angle whose cosecant is 2, or sorry, the square root of 2. Since the cosecant is the reciprocal of the sine, it's the same as saying that you're finding the angle whose sine is 1 over the square root of 2, or because we can't leave it like that, we have to simplify it to the square root of 2 over 2. Again, using our beautiful unit circle, where is our sine? The square root of 2 over 2. Okay? Well, the square root of 2 over 2 is right here. Our angle is 45 degrees, or pi over 4. All right, so let's just look at that one more time. The arc cosecant of the square root of 2. You're finding an angle in the range of 0 to pi, so it's got to be in the top part of our unit circle, whose cosecant is the square root of 2. An angle whose cosecant is the square root of 2. That's how we kind of have to think about reading this when it says arc. The angle whose cosecant is the square root of 2. Cosecant is 1 over sine. So it's the same as the sine of 1 over the square root of 2, which we have to simplify to the square root of 2 over 2, whose sine is the square root of 2 over 2, 45 degrees, or pi over 4. Okay? Okay. Nice and slow. Let's do this next part, the inverse secant function. Using the cosine graph to help us. So they have the sine graph on here. The cosine they're doing in a dotted line. Not real specifics on why that is, but they've drawn the cosine in this dotted line. And they are graphing the reciprocal of that, the secant, and it results in this graph, right? From 0 to pi over 2. Now we have some asymptotes, right? Just like we did on the pi, or on the sine over here, okay? Let's turn the page. Reflecting the graph of the secant, so now remember they changed the way the graph looks. I wish they would just keep them the same. But remember the secant is this orange one, and here, you know, it started at 1, but here for some reason they start at -2. It should be here at -1. That one you might want to draw in. That's up to you. I don't know. But reflecting it, the secant function from 0 to pi over the x equals y, so now we're finding the inverse, you get the graph of the inverse, where the orange in my pencil mark is the secant, and the inverse is in the red. Now, because we had an asymptote right here at pi over 2, it becomes an asymptote here at pi over 2, which is about 1/2. Okay, so that's why they've marked it here at 1/2, right? A way to think about this, here is my starting point of my secant, the regular secant, right? I am at 0, 1. So that tells me that my inverse, because I have to switch my x and y, is going to be at 1, 0. Now, of course, the blocks aren't always equal, but this time it works out, right? So 1 comma 0 is where I start, and I'm going to go towards my asymptote, okay? For this one, it should have been at pi minus -1, right? The coordinate plane is pi comma -1. To flip that around, it's going to be at -1 comma pi, which is about 3.14, right? So they put it at 3, which is fine. We went -1, 3, and then we went towards our asymptote. So that's how they got that one. Now, again, this is on, I forgot the page number. Page something or other over here. 58, no, 56, yeah, 56, right? This is on page 56. Just like the cotangent, the arc cotangent will be as well. All of that stuff is very easily referenceable. Please do that, okay? Now, let's finish talking about this graph. It says, note that the secant function has a vertical asymptote at pi over 2. Therefore, the graph of its inverse has a horizontal asymptote at pi over 2. Because the range of secant of x does not include values between -1 and 1, right? Here, we don't have any values between -1 and 1, right? This shouldn't be it. That's why I said this, they misgraphed this, it's fine. But between -1 and 1, there are no values. We're going the other direction, right? Therefore, when we flip it around, we're not going to have any values here between -1 and 1. Here it was y couldn't be between -1 and 1. So when we switch it, then, of course, x can't be between -1 and 1. All right? So that is the inverse of the secant. Continuing here, we have the inverse of the cotangent. So remember, the tangent starts low and goes high, right? The cotangent, therefore, starts high and goes low. When we take the inverse of that around our y equals x axis, it becomes this pretzel-y thing. Now, I didn't check the specifics of this with the graph on page 56, I think it was, just because this craziness going on here, okay? We will not be graphing these for the most part, so let's not get too freaked out about what these graphs look like. Yeah, let's not worry about it, okay? All right. If you have a graphing calculator, you can always put in the formula and see what that looks like. If you don't have a graphing calculator, Desmos, it's an app that I use. It's on my phone. I'd show it to you, but I'm using my phone to record. I think it's Desmos, is a graphing calculator app that you can get on your phone for free, I'm pretty sure. And it's pretty nice, too, to reference for these things if you're trying to get a graph, okay? So if you don't have a graphing calculator, don't want to spend $100 or whatever, check out that app. It's a pretty nice one. All right. Not sponsored, but okay. Example here. Simplify the arc secant of 1/2. Okay. Since 1/2 is not in the domain, remember, because we can't, in the secant, we can't be between 1 and -1. So since 1/2 is not in the domain of the inverse secant function, there is no solution. So it's important, and this is on that page 68. I made a little note card for myself. For the arc secant and the arc cosecant, right, we have these restrictions. And 1/2, it falls between these restrictions. X has to be less than -1, less than or equal to, or greater than or equal to 1. If something falls in between there, then there is no solution because it doesn't fit. Okay, so you can reference page 56, or I made a little note for myself. Next example then. For here we have evaluate the tangent of the arc cosine of 4/5. Okay, 4/5 is the domain of the arc cosine. That's telling us what the cosine is, right? So if we set up a little angle, cosine, right, is adjacent over hypotenuse. So we're looking for the angle whose cosine is 4/5. So 4/5, we can solve for the, using Pythagorean theorem, we can solve for the third side, which this is just a special triangle, 3, 4, 5, right? Right triangle. And then we want the tangent of that. The tangent is going to be opposite over hypotenuse, so the answer is 3/4. So some of these seem like this part kind of seems hard, right? Confusing. But when we get into the work, it's not so bad. All right. Let's take a look at the top of page 41. Simplify the arc cotangent of -1. Okay. It says -1 is in the domain of the arc cotangent. They wrote it all out there. So you will have a solution. All right. Now, this is where that chart, let me grab it again, on page 75 that I need to make a copy of apparently, in Unit 3 will come in handy, right? So it says, you know that if the angles with a cotangent value of -1 are in quadrant 3 and 4, because, 2 and 4, because that's the only place the tangent's negative, it's the only place the cotangent is going to be negative, right? When the tangent is 1, the degree is 45. When it's -1, it's going to be the same. The reference angle is 45 degrees, okay, or pi over 4. And it says since the range of the arc cotangent function is 0 to pi, you must use the angle in quadrant 2. Remember, 0 to pi, that's my other reference here, is this unit circle. 0 to pi is this top half, okay? Tangent is only negative in quadrant 2, okay? The 45-degree angle there, the 45-degree reference angle, takes us to 3 pi over 4. So the angle is 135 degrees, or 3 pi over 4 is the solution to that. All right? I know we're using a lot of references, and by all means, use your references. They're important and useful. Let's not just dismiss them because they were in a different book. All math always builds, so let's continue to use those things. Over here, it asks us to evaluate the cotangent of the arctangent of 5. Again, this is one of those trickety ones because these are kind of opposite things. You can read it as the arctangent of 5 is the angle whose tangent is 5. So the angle whose tangent is 5, they want the cotangent of that. Well, the cotangent is 1 over the tangent. So the answer is 1 over 5. Okay? They don't cancel each other because they're not exactly the same, but we just 1 over 5. The cotangent of 5 is 1 over 5. All right? Okay, let's do a couple of these problems together. Problem number 213 asks us to simplify the arc cosecant of 2. The angle whose cosecant is 2. Cosecant is 1 over sine. So 1 over 2, right? We take the reciprocal. So where is our sine? 1 over 2. Here's our reference angle, our unit circle again. My sine is 1 over 2, or 1/2, at pi over 6. So the answer is C, pi over 6. Okay? For the next one, it says simplify the arc cosecant of the sine of pi over 6. So pi over 6, again, is 1/2, right? But the angle whose cosecant is 1/2 is actually an undefined thing because remember, for our cosecant, we can't fall in between the ones. We cannot be in between the ones. So that actually becomes undefined. When it's 1/2, it's undefined because it's in between the ones. Okay, so that's letter A. Let's turn the page and look at a couple more. Looking at problem number 16 here. It says simplify the arc cosecant of the square root of 3 over 2. So the square root of 3 over 2, again, if we did it on our calculator, is less than 1. And again, for our arc cosecant, we can't be in between the ones, right? So this section, for some reason, loves these undefined answers. And so this answer is A, undefined. For 17, they want us to simplify the cosecant of the arc cosine of 1. So this is saying that the angle whose cosine is 1, the angle whose cosine is 1 is 0. The cosecant of 0 would be 1 over 0, and 1 over 0 is undefined. So the answer is A. They like their undefineds here. Looking at number 218, it says the general solution. So they're asking for, just as you can see, the general solution, not one specific answer, just a general solution to y equals the arcsecant of 1. Well, the angle whose secant is 1 is the angle whose cosine is 1, right? Because if the cosine is 1, the secant is 1. That angle is right here at 0 or 2 pi. So for the general solution, it's just going to be plus or minus 2 pi. I don't like that they put the k in here, but basically it's multiples of 2 pi, right? So plus or minus 2 pi k, which is letter C. All right, so that's just the general solution, right? You're going to go ahead and finish the rest of these on your own and whatever we didn't do on the page before this, page 41. And then you can meet me back here for the last part of this section. The last part of section 2 begins on page 43, and it's called trigonometric equations. So we're going to kind of shift gears a little bit and look kind of at algebraically at these trigonometric equations. It says in the equation sine of x equals 1/2, the variable x represents the angle whose sine is 1/2. Okay, that's how we can rewrite this into words, basically. The angle whose sine is 1/2. Recall that a way to express the angles whose sine is 1/2 is also the x equals the arcsine of 1/2. Okay, so they've just taken this and this are the exact same thing. All right. It says, therefore, so let me read through this. So this happens to be a special angle, and the special angles were on this chart in book 3, page 75. This chart is the chart of special angles. Okay, basically 30, 45, 60s, and 90s. Okay, and multiples thereof. So it's a special angle, 30 degrees, pi over 6. In addition, sine is positive in the second quadrant, so 150 degrees is the same as the sine of 30 degrees, which is the same as 1/2. In fact, because the trig functions are periodic, there are infinite numbers of angles whose sine is 1/2. Each time 2 pi is added to or subtracted from these angles, you get a coterminal angle, which we did back in book 3, right? Therefore, you have a general solution to the equation of 30 degrees plus or minus 2k pi, or 150 degrees plus or minus 2k pi. This is the general solution for this, okay? But it says here, do not confuse the inverse function with taking the inverse to solve an equation. It says this little chart might help you understand what they're talking about. So the square root of 4 equals x. If we solve that, it looks like this, right? X equals plus or minus 2. Okay, because that's what the square root of 4 is. The arcsine of 1/2 equals 30 degrees. Because the sine of x equals 1/2, then x equals 30 degrees plus or minus. It's that whole spiel here, okay? Basically, this is telling us we're going to have more than one answer going forward, okay? Evaluating the inverse trig expression gives a single solution, but there are infinite number of solutions to the equation, is what they're saying. Okay. Before, over here, we were limiting, remember, our range so that we would only have one answer. This section is not quite, we're not doing that really. We are, but they're, obviously they're limiting it to the entire unit circle, one revolution, right? Okay. Properties of equality. When an equation contains a single trig function to the first degree, you can use properties of equality to isolate the trig function. Once the trig function is isolated, the inverse can be used to determine the angle measure in the solution set. And it sounds complicated, but it's just really stuff we've done back in algebra and algebra 2. So we've done the inverse in this capacity many, many times, right? So let's turn the page. Solving a trig equation requires these things. Isolating the trig function, just like we would solve for x, right? And then solving for the angular measure. All right, the properties of equality allow you to do step 1. The inverse and knowledge of reference angles, important, don't forget your reference angles, allows you to do step 2. So here's my example. Solve 2 times the cosine of x plus 4 equals 5 for the unit circle. Do not go beyond 1 revolution, okay? Well, we are trying to get the cosine of x by itself. That's our variable, okay? So we're trying to get that by itself. First step, subtract 4 from both sides. We get 2 cosine of x equals 1. 2 is being multiplied by the cosine of x. We're going to do the opposite and divide, right? So we get the cosine of x is 1/2. Now we need to find the angle measurement using the inverse. What angle of x, what measurement of x has a cosine of 1/2? Unit circle time. Which of these has a cosine of 1/2? Remember, the cosine is the first term in our ordered pair. The cosine 1/2 is at pi over 3. That's one answer. Remember, they're talking about the whole circle here. So where else does our cosine have a positive 1/2? Well, another positive 1/2 is over here at 5 pi over 3. So if we're leaving it in radian form, it's pi over 3 and 5 pi over 3. I don't see that, yeah, so this tells us what form. This is radians, so our answer should be in radians, okay? This next example is degrees, so our answer will be in degrees. All right, looking at this next example. Solve 2 cosecant of theta minus or equals -1 for 0 to 360 degrees. Okay, 2 is being multiplied. We're going to divide. Since the cosecant is the reciprocal of the sine, the cosecant of -1/2 is the same as the sine of -2. Okay, now the angle measures, there's no such thing as the sine of -2. That doesn't exist. So this solution set is empty, right? It's not that there is no answer, it's undefined. It's just an empty solution set because it's out of range, right? Okay. They're going to throw some of those in, so be aware, right? They've been doing it all day so far. Top of the second column here on page 44. Solve 3 cotangent of x minus 7 equals -5 to the nearest degree on the degree scale. Okay, now we're talking about degrees. We want this cotangent by itself, so we're going to add 7 to both sides. Then we're going to divide by 3. So cotangent of x equals 2 over 3. It says here to find the measurement, you'll need a calculator to determine. Make sure your calculator is back on degree mode. I was working this out here, and I still had mine on radian mode, and I was starting to lose it because I was like, why is this not working? But because I had it in the wrong mode. So make sure from last week, yours is back in degree mode. So if we take the reciprocal of 2 over 3, we get 3 over 2, which is 1/2, right? 3 divided by 2 is 1/2. So if we take the inverse tangent of that answer, 1/2, close your parentheses, you'll see that it is 56.3, but we're just going to round it to the nearest degree because that's what it asks us to do. 56 degrees. Now, that is for our cotangent, right? 56 degrees, but tangent is also positive in the third quadrant, so they add 180 degrees to get 236, which is also the solution. So now there are 2 solutions, 56 and 236. All right? So that's the first part of working these out. Very algebraic, right? If you think of your trig function as a variable, slide right through. All right? Let's take a look at the next part then here. The zero product property. Zero product property, we've done years, right? You factor out a common factor. That left us with x for this problem here. Left us with x times the quantity, x minus 3. We set each one equal to 0 and solve. Okay? Very simple. The same can be done for these trigonometric properties. Now this example finishes at the top of the next column, which drives me crazy, but let's just work through it. It says here, solve sine of x times cosine x equals the sine of x for 0 through pi, or 2 pi, right? 1 revolution. Now it says, note that while there is a single variable in the equation x, there are two trig functions, right? This function and this function. Algebraic properties do not allow you to divide by an unknown because there is a possibility it could be 0. So you can't divide both sides by sine and get cosine of x equals 1, right? That's what it's saying. You can't do that. Top of the next page here, page 45, to finish this example. So because there are two terms, each having a common factor of sine, that's what we want us to remove. So they put all the terms on the same side of the equal sign. They have the sign in common, so they factored that out. So now you have the sine of x times the quantity cosine x minus 1. Well, now that are equals 0, right? So now we know that the sine of x equals 0 and the cosine x minus 1 equals 0. Well, given this domain, the sine of x equals 0, so x must be 0 or pi. Right, on our unit circle. I'm going to slide the whole thing over here. 0 is pi. Right here, sorry. 0 is pi. 0 is 0, or 0 is pi. Okay. The cosine of negative 1 equals 0. We add the 1 to both sides. So where is our cosine equal to 1? Well, our cosine is 1 here. At 0 again. So we have two answers, 0 and pi. It's going to be either 0 or it's going to be pi. Okay? Now, that was pretty basic, zero product property. Not too challenging, but let's look at this quadratic equations. Quadratic equations. We've learned many different ways to solve these. Okay? Usually by factoring, but sometimes that doesn't work. We'll talk about that in a second. But here are some examples of quadratic equations. Cosine squared of x equals 1/2. 3 cotangent squared of x plus 1 equals 2, right? These are examples. It says when the equation does not have the trig function to the first power, these two equations, these first two, do not have a trig to the first power like these two do. Right? It's just a square and a number. You can use the square root property to solve. Here's our example, okay? 3 times tangent squared of x minus 1 equals 0. They want radians. We're going to add 1 to both sides. Of course, it finishes on the top of the next column. Now we have, we only had 3 tangent squared x equals 1. They divided by 3. The top of the column, and ended up with the tangent squared x equals 1/3. To undo a square, we take the square root. So they took the square root of both sides. Got the tangent of x is equal to plus or minus the square root of 1/3. Now, the square root of 1 over the square root of 3, we cannot leave, right? So we have to multiply it by 1 in the form of the square root of 3 over 3, and that's how they got the square root of 3 over 3. Square root of 3 over the square root of 3. These two gave us the square root of 3. Square root of 3 times the square root of 3 is 3. So we end up with plus or minus the square root of 3 over 3. Now it says, find the angle measures. If we look at our chart in Unit 3, page 75, where is our positive and negative, technically, square root of 3 over 3? Well, we're talking about tangent, so the tangent of the square root of 3 over 3 is at pi over 6, because we're talking about radians here, so pi over 6. We should recognize it says, I'm not a big fan of memorizing things, right? So I don't have, it's not a priority to me, but if you don't recognize it, then at least be able to find it, right? That's my goal here. So pi over 6 is where? Right here, right? But it says the tangent values are plus or minus, right? It was plus or minus the square root of 3 over 3. So there should be 4 answers, because in every quadrant, there is either a positive or a negative square root of 3 over 3, right? So we have to find all of those things. So the first one here is pi over 6. The next one is here at 5 pi over 6. Basically, add a pi. Pi over 6. I don't want to write on there. Let me see if I got a scratch paper here. Of course, they're stuck together. Okay. Pi over 6. Oh, my word. Plus pi, because we want to move into this next section, right? Becomes pi over 6. I guess not plus pi. We're going to subtract it from pi because that's our next stop, right? So it's, oh my gosh, pi minus pi over 6. Jeez. Okay. So this is going to be 6 pi over 6, right? That's how we got pi. Minus pi over 6 gives me 5 pi over 6. So that's that part. Then here is where we add the pi over 6, because now we want to go into this quadrant. So now it's pi plus pi over 6, or 6 pi over 6 plus pi over 6, which gives me 7 pi over 6, okay? And then over here, we want to take our 2 pi and subtract pi over 6. 2 pi minus pi over 6, or 12 pi over 6 minus pi over 6, which is 11 pi over 6. Okay, so those are our 4 answers. Because it's plus or minus square root of 3 over 3, it's landing in every quadrant. And so we need to figure out all of the quadrant answers. All right, and they've done that right here a lot better than I did. All right, okay, so this chart, important charts we want to keep with us so that we have access to them all the time. All right, my paper fell down. Okay, now it says when the equation includes the trig function to the first power, you can often use factoring to solve. Okay, solve the secant squared of theta minus the secant of theta minus 2 equals 0 for the whole unit circle radians, right? Well, they're asking what factors of -2 add up to give me a -1. Well, it's going to be a -2 and a +1, right? And then our secant, because it's a perfect square, gets pulled apart, just like if we were factoring x squared minus x minus 2. Exact same thing, okay? And then we set each part equal to 0. So secant minus 2 has to equal 0, and secant plus 1 has to equal 0. We slide them over. Now, the secant equals 2, okay? Then the cosine is 1/2 because the secant is 1 over the cosine. So the cosine is 1/2, and theta then is pi over 3 based on our unit circle. It's positive in quadrant 1/2, right? It's positive also in quadrant 4. So pi 5 pi over 3 is also a solution. Now the secant equaling -1, then the cosine, of course, is -1, and that tells us we're at pi. The quadrantal angle, and it says it is in a quadrantal angle, and it's the only one with a cosine value of -1. So we don't have a second one that time. So our answer has 3 answers this time. Square root of pi over 3, pi, and 5 pi over 3. Okay, let's turn the page. For the top of page 46, there is this might help, like if you substitute in a regular variable for the trigonometric term, then it might be easier for you to understand. I'm just going to go ahead with these trigonometric terms. Solving the cotangent to the 4th of x minus 4 cotangent squared of x plus 3. What factors of 3, and there aren't many, right? It's just 1 and 3, are going to multiply together to give me a +3, but add up to a -4? Well, that's going to be a -1 and a -3. Because this is a cotangent to the 4th, it splits up into 2 cotangent squareds, right? We set both of those equal to 0. We get cotangent squared equals 1. So we take the square root. Cotangent is plus or minus 1. Here we get the cotangent squared equals 3. We take the square root and get the cotangent equal to plus or minus the square root of 3. And then we find those sets of points. And those sets of points are vast. There are many points that meet both of those criteria. All right. So use your unit circle and find all those points. It's just the work that's got to be put in, okay? Now it says not all quadratic expressions are factorable. Just like in regular algebra, right? We couldn't factor everything. Sometimes we had to use the quadratic formula, which is here at the top of the page. Now, using the quadratic formula to solve trig equations works in much the same way, but there is still a difference. The results do not give us the solution. Rather, the results in the values of the trig function are the values of the trig function. You must still solve for the angle measure, okay? Here's our example. Solve. 2 times the cosine squared of x equals 4 cosine x minus 1. We've got to move everything on to one side of the equal sign, right? Just like we normally would. What is our ABC? Now, our A is 2, our B is -4, and our C is 1. Now we can put these into our quadratic equation, the top of the next page. 4 plus or minus, well, it's actually minus B, right? So it's minus 4, which becomes positive, plus or minus 4 squared. You can see that they've done the quadratic equation, okay? I'm not going to try to read everything off because the way it's going today, I'm just going to stumble over it. We end up with the cosine of x equaling, because that's where we were, right? Cosine, 2 plus or minus the square root of 2 over 2. Now we're going to have to find out the decimal equivalence, right? Because that's just what we need to do. And then we take the inverse, or the calculator one is where these things get a little confused, right? Cosine negative, the arc cosine, to figure out what the actual angle measures are, okay? There is not a solution for this 1.7 because, remember, cosine can only be a 1. It doesn't go higher than a 1, so this is not a valid solution. So this is the only one that's valid. It ends up being 73 degrees. But remember, our cosine is positive in more than one place when we're talking about the whole circle, the whole unit circle. And so that other place is at 287 degrees, all right? Okay, that's that. So let's take a look at these next problems together, right? 2.28. If the secant of x is -2, in which two quadrants does the solution lie? Okay, the secant is negative, but the secant is also the cosine, right? So where is my cosine negative? Well, it's negative in the second and third quadrants. So the answer is C. Not really a lot of math to do here. That's just where it is, where it works out, right? Okay, 29. If 2/3 tangent of x plus 15 equals -9, then the tangent is, all right, we're going to work on it over here in the corner. They don't exactly give you a lot of space. So I'm going to go ahead and subtract 15 from both sides. So I get 2/3 the tangent of x is equal to -24, okay? Because subtract 15, -9, minus 15 is -24. To get rid of a fraction, we're going to multiply by the reciprocal, which is 3 over 2. Oh, I don't have space. 3 over 2, right? These cancel. So I get that the tangent of x, which is what we're solving for, is equal to 24 times 3 over 2, -24 times 3 over 2. Well, I can reduce this 2 to a 1 and this to a 12. So -12 times 3 is a -36. So the answer is D. Okay. For number 30, find the solution to the equation, or solution set, sorry, of the equation, negative tangent A equals -1. Well, if I have negative tangent of A equals -1, I'm going to divide by that negative, right? And get the tangent of A equal to 1. So I'm on the unit circle in radians. Where is my tangent equal to, grabbing my unit circle here. Where is my tangent equal to 1? My tangent is equal to 1, and this is the chart. Again, unit 3, page 75, here at pi over 4. Okay, so I know pi over 4 is one part of it, but where else is my tangent positive? My tangent is also positive in quadrant 3. Quadrant 3 at our 45-degree reference angle is 5 pi over 4. That's this one here, okay? This is the reference angle for quadrant 3. So it's also 5 pi over 4. So my answer is pi over 4 and 5 pi over 4, so letter B. All right, let's turn the page. Taking a look at problem number 36, it says, how many solutions does the equation the cosecant squared of theta equals 4 have for the unit circle? Well, if we take the square root, right, we get the cosecant of theta equals the square root of 4, or plus or minus 2. And since we have plus or minus 2, that covers all the quadrants, all 4 of them. So there's going to be 4 solutions to this equation. They're not asking what they are, they're just asking how many. So there's 4. For problem number 37, it says, find the solution set for the equation sine squared x minus 2 sine x minus 3 equals 0 for the whole unit circle in degrees. We are going to factor this, okay? What two numbers multiply together to give us a -3, but add up to give us a -2? Well, that's going to be the sine of x minus 3 times the quantity times the sine of x plus 1. All right, so now I can say the sine of x minus 3 equals 0, and the sine of x plus 1 equals 0. Solving this first part, I get the sine of x equals -3. And this second one, I get sine of x equals -1. Now, I can't have the sine of x equal -3 because that is outside of the realm of sine. Using my unit circle, which I kept right here. Sorry, it's a lot to juggle in a tight space that I have to work with. Using my unit circle, where is my sine? -1. Remember, the sine is the second number. And so -1 is down here at 270 degrees. So that is my answer. There is not more than 1 for that this time. Okay. Keep my unit circle off to the side here. Let's take a look at problem number 38. Solve the equation tangent squared of beta equals 4 for 0 to 90 degrees round to the nearest degree. Okay. So I'm going to take the square root and find that tangent of beta is equal to plus or minus 2, right? Take the square root of both sides. And now we have to think. We want between 0 and 90. I'm going to have to set up a thing, right? The tangent is 2. This is my angle. The reference angle tells me if my tangent is 2, that opposite over adjacent is 2. So this has to be 2 and this has to be 1, right? So 1 squared plus 2 squared equals c squared. 5 equals c squared, so c equals the square root of 5, okay? I don't know that that was necessary, but this is kind of the path we're walking down a little bit. Okay, looking at it, we know it's not necessary. Sorry. It just was the first thing that came to mind. We don't want the negative because that falls outside of our range here. If we turn on our calculator and we do the inverse tangent of 2 and hit equals, we will see that it is 63 degrees, which is what they're asking for. So it is important to make sure you actually read and understand the instructions, okay? Because then we wouldn't have wasted our time doing this over here. Wasn't necessary, okay? All we had to do was, what angle measure has a tangent of positive 2? Well, that's a 63 degrees, all right? Okay. Go ahead and finish those couple over here that we didn't do together. And that is it for section 2, okay? If you have any questions, do not hesitate to contact me. I know this section seemed like it was all over the place. But if you have questions, let me know. Otherwise, until next time.